Neuroprosthetics implies that the device is connected to the nervous system. What caused that loss? So for example, you could have loss of motor and sensory function because of spinal cord injury. Motor is connected to a nerve fiber, so every time the brain sends some command through the nerve, it activates the motor. Or you could have some sensors applied on the hand that when stimulated conveys information through the nerve and from the nerve back to the brain. It's very difficult to come out with one solution that fits everybody. And so you have to be very aware of what matters to the particular user. Maybe find modules that you can replace depending on, say, I'm in a particular sport and I want to go climbing. Well, we could put an accessory that will allow you to go rock climbing. You have a person who's paralyzed from the neck down, being able to grasp an object, put it to her mouth, interact with the environment without any control whatsoever from her muscles. That's pretty amazing. If you look back in the last 15 years, we're doing things now that we could not have imagined possible. The future is definitely exciting and promising. So in this lab, we perform experiments where we stimulate the brain, and we use this particular tool, which is a coil that is used to induce current, electrical current inside the brain. Current within the skull can do a couple of things. It can excite the particular part of the brain you're stimulating or you're in contact with, or inhibit it. It's also used in the clinic. It is either to assess the excitability of the brain, which may be lowered in some conditions, for example stroke, or in the lab for research purposes. What we use this for is a system identification technique. What that means is that you might have an idea of the network in the cortex. So the cortex is the most superficial layer of the brain. And so you might say, for example, that point A and B on the cortex are connected, and that this connection between A and B allows a given function. Say, for example, in my lab, we look at grasping. And so let's say that your ability to hold an object and preventing the object from slipping is because this point A and B in the brain are connected to each other. This could help people that don't have their hands, translatable amputees, for example. And so it was redesigned in a way that now you can control this using electrical activity of your forearm muscles. The design of this hand is based on experimental observations of how humans control their hand to grasp different objects. And so what this does, every time the motor is activated, the entire hand moves together in a way that resembles how the human hand moves. And the advantage of doing that is that it's very simple to control. That is that the hand keeps moving until it encounters a resistance. And then we record the electrical activity, and this is called EEG, electroencephalography. And then you can record in real time the different event-related potentials, which means how this activity in the brain changes as a function of the task you're doing, whether you're using a memory of a particular task or a particular thing you have to do, feedback you are receiving, for example, when you touch an object, and so forth.
So if an individual presents a project to us in which they require a prosthetic limb, the first step is acquiring the data related to their pre-existing tissue. So we'll use something similar to this photogrammetry setup. We have multiple cameras at different points, and we can combine their perspectives to create a 3D model. So someone might extend their pre-existing tissue into a space like this where we have a camera array. We capture the data, simultaneous snapshots from each perspective, and combine each perspective to create a 3D model where we can understand exactly the shape of the tissue as it stands now. From there, we'll create a 3D model representation of a prosthetic limb that we can then attach to the person's current tissue. So after we've captured the data for a prosthetic limb patient and have designed a 3D model that fits to their specific mobility appearances, we're able to create a 3D model and 3D print the different pieces of the assembly. We can produce a 3D printed object that is satisfying the person's range of mobility. So for instance, in this example, someone that has at least 30% wrist mobility and doesn't have any fingers can use this model. When they bend their wrist, they can then grasp an object. And we can custom tailor fit the fittings so that it feels like a glove. Past that, there are other types of prosthetic limb projects for different types of mobility. For instance, if the tissue starts at the elbow joint, we can create prosthetic limbs that use the range of motion they're capable of producing in order to make a relevant limb that is functional for their purposes. The future of 3D printing in the realm of bioengineering is very exciting. Whereas right now, we have from basic to robotic models of prosthetic limbs that are more affordable and accessible than ever before. We can look to the future and hypothesize we're going to have limbs that are more responsive, more dexterous, stronger than ever before, truly creating superhuman abilities. With our knowledge of these prosthetic limbs, technology that incorporates with our own nervous system, we'll have something that seems like you can't tell real from prosthetic. Very exciting for people currently in need, as they won't have to have a stigma attached to them anymore, and if anything, they'll be sought after more for their enhanced abilities. So as we collaborate together in advancing these kinds of technologies in bioengineering, we're enabling the future of individuals that were previously disabled and are now considered potentially far more powerful than the average user.